Welcome to next class. Okay, so today we'll go for the next concept of the unit 4, that is the magnetic property. So in magnetic property, so we will take the concept of spinels. Okay, so in the spinels we are going to see learn there are three types, that is your normal spinels, inverse spinel and mixed spinels. Okay, so these three types we are going to learn. Okay, so very simple. So it depends on the type of the crystal solids. Okay, so crystal solid, for example, if you take the type that is AB to X4. Okay, so where A will take as a divalent cation, okay, that is A plus 2, and B we will take it as a trivalent cation B plus 3. Okay, and X may be any anion like oxygen, sulfur, fluorine, okay, fluorine or selenium, etc., like this. So this we can take it at, and we can see that whenever the crystal solid we are taking, there are two types of voids, that is one octahedral void and tetrahedral voids. Okay, and this is nothing but fitting of these both cations into this voids. Okay, and when they fit into these voids, we can consider them into these three different types here. So how they fit into them. Now if you see, for example, if you take this divalent anion A plus 2, so if it goes into a tetrahedral void, okay, so you think that if it is in a tetrahedral void and the trivalent ion B plus 3, okay, if it is going to octahedral void, OH I am representing here, octahedral void, then the spinel we call it as a normal spinel, very simple way. So the spinel will be the normal spinel. Okay, so where divalent is occupying the tetrahedral sites and the trivalent is occupying the octahedral sites, so we call it as a normal spinel. And if we take in the reverse way, then it's called as inverse spinel. Okay, now if we in the inverse spinel, what is the inverse spinel now? So reverse it is obviously now here it is A plus 2 going tetrahedral wide. So inverse sphere you can see A plus 2, that is your divalent if it is enters into the octahedral wide, and the trivalent B plus 3 enters to the tetrahedral wide here. Okay, so then we can say that this is inverse. But what happens here, one thing you have to keep in the mind, see that A plus 2 divalent is yeah, definitely is going to octahedral wide here, fixing here, and this trivalent cation, what is there, B plus 3, so they goes into both here, and tetrahedral, half of the B plus 3 and half of the B plus 3 goes to octahedral wide. Okay, so this is very much important here, and such type we call it as a inverse spinel. There is some of the trivalent is introduced into these octahedral wides, and some of the trivalent is introduced into the tetrahedral wides. Okay, so that we call it as a inverse spinel. So when we learn with the examples, then definitely we'll come to understand this. Okay, and the mixed spinel you can see, then what is a mixed spinel, then both when it is mixed, so a normal as well as inverse spinel, when you see the conditions in one crystallized, then we call it as a mixed spinel. Okay, so these all things we can learn it here. Now the if you see, and even these three types of spinels, normal, inverse and mixed, can be determined with the help of CFSC, that is your crystal field stabilizing energy. Okay, so this thing also you should remember here. So we can identify this as a crystal field stabilizing energy. For example, if you take the trivalent anion, so if B plus 3, you will take this trivalent anion CFSE in octahedral field. Okay, CFSE, if this is greater than divalent A plus 2, okay, that divalent CFSE, I will write CFSE here, same thing, octahedral field, then what will happen here, then such crystal we called it as a normal crystal. Okay, then in such crystal we called it as a normal crystals. Okay, so the CFFC of trivalent ion should be greater than divalent ion CFSE, then it is a normal crystal. So you should remember this. Okay, this is also very reverse of this is inverse crystal. So that's what reverse of you take this now here. So divalent ion CFSC in octahedral field, if it is greater then trivalent ion B plus 3 octahedral field CFSE, then it is inverse, inverse spinel. Okay, so this is what we can show. So divalent CFFC is greater than the trivalent inverse figure. For example, you take, so if you take the example of this one, okay, Fe, this is a common example we give, Fe 204, okay, Fe 204, this one. Okay, so if you take this example here, Fe 204, okay, so this is one type of this one where this Fe is present in +2 state here, +2 state, and this Fe is present in +3 state. Okay, this Fe is present in +3 state. Now I will take this 2 Fe here, so this Fe is in +2 state and this Fe is in +3 state. This Fe is in +3 state. Okay, no doubt they are having two Fe 204, so 2 Fe is in +3 state and 1 Fe is in +2 state. Okay, so you can take it in this way. Okay, now what you say, this +2 state is what now? This is D6 octahedral. Okay, and +3 is nothing but D5 octahedral, and D5 system, you know that CFSC is equal to 0 always. Okay, so D5, that is, if you see like this, if you split and do it, so 1 2 3 4 5, so this always you can see the this one has a minus 0.4 delta naught, minus 0.4 delta naught, and above we are having the plus 0.6 delta naught value. Okay, so 6 2s are 12 and 4 3s are 12, so if you do CFC going to be 0 here in D5 system, and in D6 system definitely is not equal to 0. Okay, in D6 system, so you are having the FE not equal to 0. Now what is the condition here? That is your Fe plus 2 CFSE value is greater than Fe plus 3. Okay, so this is a condition in octahedral field here. And what is that we learned here? So in this case, if Fe plus 2 CFS is greater than 3, then it is an inverse spinel. Is it right? So that's why straight away this compound what we are learning is an inverse spinel. So we call it as a inverse spinel. So this is how very simple we can explain this spinels. Okay, now if you go for some of the points, okay, some of the points to be remembered. Now see, simple, if both A plus 2 and B plus 3, so if both the divalent and trivalent B plus 3, okay, if they are having of non-transition elements, if they are made up of non-transition elements, okay, like now just we have seen that sodium, magnesium, gallium, something like that. So okay, non-transition elements, you know that what are transition elements, so they are termed as normal. So very simple, you just name it as a normal spinels. Okay, so this is what we can keep in the mind. Okay, now if you go for some of another configuration like D3 and D8 configuration, okay, so obviously this D3 D8 configuration, if you see, so they are having highest CFFC value, they are having the highest CFSE value, so this also you have to keep in mind. Okay, D3 and D8. Okay, so this, when it comes in any of the problem solution, so they are having the highest CFSE value, and always this prefer to go in the octahedral voids. Okay, they are going to in the octahedral voids. Okay, then you calculate according to another metal ion, and you can come to conclusion whether it is normal, it's a normal spinel or reverse spinel, inverse spinel. Okay, so this, but whenever it comes in D3 D8 configuration, just to take into account that it is a highest highest CFSE value, so in and that too they are going to fit in the octahedral voids. Okay, so this is what you have to keep in the mind. Now another condition will be what, if A plus 2, if you take this divalent ion is non-transition. Okay, it's a non-transition element. Okay, and B plus 3, that is trivalent, is a transition element, is a transition element. What will be the condition? This is very much important, is a transition elements. Okay, and if you take for the system, so system also is, configuration also is important. D1, D2, D3, D4, D5 you don't take, D5 is out, D6, D7, D8, D9, D10 also you can keep out, D0 also you can keep out. Okay, so if you see that A plus 2 is non-transition elements and B plus 3 is transition elements, usually this configuration, then you can take it as a normal spinels. Okay, so such this we can take it as a normal spinels. Okay, so they will be normal, and D0, D5, D10 they have 0 CFS, you know that CFSC, this configuration have 0 CFSC. So this is what one thing you can keep in the mind. Now reverse of this, that is A plus 2, if I take divalent as a transition element, if this is a transition metal A plus 2, and again same configuration, that is D1, D2, D3, D4, D5, D9. Okay, same configuration as here, up D1 to D9. Okay, taking out these three. So what will happen here, if A plus 2 divalent is a transition element and A plus 3 also transition elements. Now we will take A plus 3 also transition element, both are made up of transition elements. Okay, so then it is a inverse. Then you take straight away, you can say that will give you a inverse. Okay, so but divalent also transition elements with this configuration D1 to D9, excluding D0, D5, D10, and trivalent also is a transition metal made up of transition metal, excluding these three. Then definitely you can see it will give a inverse type of spinels. Okay, and you should see that always the CFSC crystal field stabilizing energy for non-transition, whenever it will be there, it will equal to 0. Okay, so if you take magnesium, if it is there, calcium, any of the non-transition elements is there, the CFESC will be equal to 0. This thing you have to keep in the mind. Okay, now keeping all these things in the mind, so we will go for some of the examples here. So MgAl2O4, so this is what the example is here, and we know that here the magnesium is a non-transition element. Magnesium is a non-transition element and it is plus 2 state, Al plus 2 here, and here Al is in plus 3 here. Okay, and this also is a non-transition element. Both are non-transition element, Al plus 3. Okay, so when both are non-transition elements, you know CFSC of both will be 0. CF crystal field stabilization of both will be 0, and according to note or point to be remembered, so what both, if it is non-transition elements, we call it as a normal spinels. So the both this is comes to be normal spinels. Okay, so this is how we can do it. Similarly, so one more example, if you see that FeCr2O4, they have given this here in one of the paper, FeCr2O4. Okay, so now here also Fe in plus 2 state is there, and we'll bifurcate here, and Cr plus 3 state is there. Cr plus 3 state is there. So Fe plus 2 means which one? D6 system, and Cr plus 3 is D3 system here again. So no need at all. So now D3 means what? Highest CFC, because from the point we have learned D3, and what is D3? D8, highest configuration CFS will be there. So this will be highest. Okay, so obviously what will happen now here? So see, if since the highest the chromium here Cr in plus 3 state is highest, greater CFSE than iron plus 2 state here. Okay, so when this is case here, so what does the rule say? It will be normal spinel. So similarly it will be normal whenever the trivalent CFS is greater than divalent, then we call it as a normal spinel. See, this is how. Okay, so this is suddenly, by knowing the points, we can remember and we can say fast whether it is normal, reverse, or like that. In one more example, you can take of zinc. Okay, Fe2O4. Okay, third example, ZnFe2O4. Here you can take this here. Okay, now here what will happen here? Now here zinc is there and Fe plus 3 is there. Okay, so no doubt here Fe plus 3 again here, D5 system here. So D5 system again here, CF crystal field stabilization energy is 0, and this is non-transition element. This is the D10 system again, so definitely it's having a 0. So both are having CFESC crystal field stabilizing energy 0 here. Okay, but here what you have to see here, that is the size. Okay, it is a transition element size. As we go across the period, size decreases. Okay, that means zinc is having very small in size. Zinc is having very small size compared to iron here, because across the period we know that the size decreases. Okay, and this zinc now being smaller in size, they prefer to go in tetrahedral voids. Okay, they prefer for tetrahedral void, and Fe plus 3 they prefer for octahedral voids. Fe plus 3 prefer for octahedral voids. Okay, so looking at to this, this then what we can show, what we can say, that this comes under the, from the points to be remembered, this comes under the spinel of normal spinel. See, okay, so this also is very important to know whenever there is a size difference. Now here this is very small in size, this is very big in size. Okay, so this is tetrahedral plus 2 and this is plus 3 in octahedral. So in this case the spinel will be normal spinel. So size also is very much important. Is it right? For example, you see this Mn. Okay, if you see this Mn Fe2O4, one more example here, manganese and iron is there. Okay, where manganese in plus 2 state, So manganese in +2 state, bifurcate it from iron, which is +3 state. Okay, now here also both are D5 system and both have CFSC 0. Okay, both are D5 system and both have CFSC 0 here. Okay, but problem here is there is a comparable size difference between manganese and iron. So manganese and iron have very comparable size. Okay, almost size is same here, so you cannot judge here. So there is a problem now here. Okay, so when this is happening here, so we call it as a mixed spinel. So when this is a condition here, so we call it as a mixed spinel. Okay, so here some of the part remain as a normal spinel and some of the part will act as a reverse inverse spinel. So that's why we call this as a inverse spinel. So like this, in some of the concepts you should remember. So how to make this, differentiate this, the normal spinel and the inverse spinel. Okay, so like this you can do it. So some of these examples also you can take some of MgFe2O4, MgFe2O4. I think I have done this. So anyway, so magnesium is there here, bifurcate here. You know that the crystal phase stabilization energy is 0 for magnesium, and Fe+3 also same thing, it is 0. Okay, because of the D5 system. And definitely again, if you see the size of magnesium being a non-transition element and Fe+3 being a transition element, they are very comparable in size. So they are comparable in size. Okay, so almost the same, and that's why again there is a problem here, and they are termed to be mixed spinels. Okay, whenever there is comparable size and both having the CF0, then straight away you can see that they will be coming under the mixed spinel. Okay, so like this. Okay, now mixed spinel or for inverse spinel. Now so some of this will go for CFAC, we have come to know. Okay, and other factors we have come to know. So like this, I think we have cleared this what is say, three types of spinels here. Okay, so one more thing, now if there is the combination of given is nickel +2 and gallium. Okay, gallium, if they give 3, gallium +3. Okay, and both here nickel is a transition elements, no doubt this gallium is a non-transition elements. So gallium non-transition elements, so definitely the crystal field stabilization energy of gallium will be 0 here. And this is a D8 system, nickel +2 D8 system, so definitely it is not equal to 0. CFSC will not equal to 0 here. Okay, that means your divalent cation is having CFSC greater than the trivalent ion. So definitely, so this is a inverse spinel, so we commit as a inverse spinel. So like this. Okay, so this we can do. Even you can go for zinc +2 Fe+3. Okay, so if you see zinc +2 and Fe+3 combination, if they give, so zinc +2 and this is a D5 system and this is a D10 system. Okay, so both will having the CFFC 0, CFS equal to 0. Already we have done it. So since the size variable will be there, so this will come as a normal spinel, because +2 fits in the tetrahedral void and +3 in the octahedral void. So this come because of size is very small of zinc, we already done it. So normal spinel here. So like this we have so many things. Even Mn+2 Mn+3, Mn+2 Mn+3, if this combination is given, so almost Mn+2 is D5 configuration, Mn+3 is D4. Okay, and here CFSC will be equal to 0, and this has value D4, they have some value, is not equal to 0. CFFC is not equal to 0 here. So what will happen here, that is now the CFFC of Mn+2 trivalent is greater than divalent. Okay, trivalent is greater than divalent. So when this condition is there, again we can term it as a normal spinel. So like this. Okay, so in this way we can see that we can distinguish the different types of spinels here. Okay, so hope you understood this concept here. Okay, so just check it while you do this, and don't get confused. The rules you have to keep in the mind. Like in one question paper, he has of cobalt Fe2O4, and Fe2O4. Okay, so identify the condition in this two case here. So like this he has asked which spinel is this. See, cobalt here you can see, so cobalt is in +2 state here and iron is in +3 state. I will write here +3 state. Okay, so cobalt 2 means D7 configuration here, D7, and here +3 means D5 configuration. D5 means immediately you have to write crystal field stabilization energy is equal to 0, but here crystal field stabilization energy will not equal to 0. Okay, so what will happen here now, divalent, so here what become cobalt +2 divalent, CFSE greater than trivalent here, so that's why this will be inverse. Okay, so whenever divalent is greater, CFSE is greater than trivalent, then it will be inverse, then it will be inverse. Okay, so this is how, this is how. Okay, so remember this. Okay, fine, but if you see for this now Fe2O4, so here also Fe is in +2 state and one Fe +3 state. Fe+3 is D5 system, Fe+2 is D6 system, so this CFSE is 0 and this is not equal to 0. Now this CFSE, so again same thing here, so divalent is greater than trivalent, so this also inverse. That means both are inverse, both crystal structures are inverse, both crystal structure are inverse. See. Okay, so like this questions will be asked, and very carefully we have to give the answers. Okay, so this is how you can see that lot of things in the spinels we can learn here. Even the metal oxides in the metal atoms also you can see that these arrangements will be there, spinel arrangements, that also sometimes they will ask in the examinations. Okay, so and even the hybridizations also sometimes. Okay, for example you can see here Al2O3 is there, so what is happening here, Al2 is having 2 Al plus 3 state, and it is having 3O minus 2, 3O minus 2 and 3 2 Al plus 3 state it is there. Okay, if it is Al3O4, so what is now Al3O4, so one of the aluminum is in +2 state and two of the aluminum is in +3 state and 4 minus 2 ions is there. See here. Okay, now here what we are having here, so aluminum is having now two different oxidation state, so we are having here two different oxidation state of aluminum here. Okay, so one is in +2 state and one is in +3 state. Okay, so like this also we have to see that the metal ions whenever we see, so they may be of same ions, like now we are seeing they may be of same ions, like now we have done Al plus 2 and Al plus 3, so same ions is there but different oxidation state. And if you see they may be of, for example if you take Al2O4 in one of the example in up we have seen, so here what we are having here, Ni is in +2 state and aluminum is in +3 state here, so they are of different ions, the same ions, here we are having different ions, so two conditions we can see here. Okay, and the spinel arrangements you can see O minus 2 here, so these are the spinel arrangement, and they are having the FCC packing here. Okay, so face centered cubic packing of the O2 minus O minus will be there. Okay, the how many, 4, so 4 oxide ions will be there, O4 is there, so 4 oxide layer they are having the FCC packing here, and 4 oxide layer means how it is been arranged, they are arranged in 4 octahedral voids. Okay, and 4 octahedral voids means how many tetrahedral, double, that is 8 tetrahedral voids. Okay, so like this it is been arranged. Okay, so 4 octahedral voids and 8 tetrahedral voids, so always it will be there. Okay, so this is also you have to keep in the mind. So if you see here metal ions they occupy usually the whites here, how they occupy the whites here, this also is very much important. For example Al3O4. Okay, so you take this Al3O4 here, one example you will see, so always we can see here tetrahedral here, tetrahedral void, that is your +2 divalent ion tetrahedral voids. Okay, then we can see here again here +2 in octahedral void, +2 octahedral void, and again you can see here +3 again here octahedral void. Okay, so because Al3 is there, so one is here Al plus 2, here also Al plus 2 and Al plus 3, like this. Okay, so here how many tetrahedral FCC arrangement here, so how many this will be how many the in this will be there, 1/8 into 100 if you take from the crystal attached tetrahedral site, they are present in the FCS's corners. So you can see 12.5%. Okay, so this is sp3 hybridized. Okay, always sp3 hybridization will be there for the tetrahedral sites here. And if you see here the octahedral sites +3 state here, so how many will be there? I said there are 2, no? So 2 divided by 4 octahedral sites is there. So here 8 will be there because tetrahedral always 8 there. In previous I have just shown. And here 2 aluminum is there, 2 Al+3 is there here. So 2 by 4 into 100 if you do, so 80%. So like this. Okay, so this is how. And this you can see they are having the hybridization of sp3d2, sp3d2 or d2 sp3 octahedral. Okay, you know that. And tetrahedral sp3 hybridization, so you should remember this also important. Okay, so always tetrahedral whites whatever is banned, this sp3 hybridized, and the octahedral whites it is always sp3d2 or d2 sp3 hybridized. Okay, so this also you have to remember. Why? Because if you take some of the oxides of having the face centered cubic, this one for example, if you take the oxide of M3O4, you take any of the metal here where one of the metal is in +2 state here, one of the metal is in +3 state, and yes, one metal is +2 and 2 are there here. So 2 metal is in +3 state here. Okay, so here what will happen, or +3 state. Okay, so here what will happen here, this is in tetrahedral wide, so 1 m+2 will be in tetrahedral side, and m+3 in the octahedral side, and this also in the octahedral sides. But here what happens, this octahedral side sometimes some of this will be seen here in tetrahedral wides, and this tetrahedral is sometimes skipping into this octahedral wide like this. Okay, so m+3 octahedral will come here, some of the percent of this, and some of the percent of this will come here. So that type, if it happens, we even term it as a inverse spinels here. Okay, so this is very much important here. So like here, so m+2 is there, so m+3 and m+3 like this. Okay, sometimes like this. Okay, so here what will happen here now, m+2 here tetrahedral whites means we know that it will be, this is coming here in tetrahedral, that means it is having the sp3 hybridization. So this is coming here, so we are having sp3 hybridization. And this final we can see they may have sp3d2 hybridization or d2 sp3 hybridization. Okay, they are perfectly in the octahedral here, but one of the m+3s since it is introduced into this +2, so they may have sp3 hybridization. See, same thing will be there, but one of this is skipping into here, so that's why they may have sp3 hybridization. Similarly here also, since this has skipped here into this, so they may have two type of hybridization, that is your sp3d2 hybridization and one also sp3 hybridization. Okay, so like this, so mixing will be there here. So okay, so one will be in tetrahedral and octahedral wide. Octahedral will skip here, from tetrahedral will skip here, so like this. Okay, or you can take sp3d2 or d2 sp3d2 and sp3d2, something like that. Okay, so this way, so if you see the hybridization here, so you can see that the mixing of the hybridization will be there. Okay, so apart from this we are going to have the term like spinal parameters. Okay, so you are going to have the term like spinal parameter. This is also very much important. Okay, so and it is termed in terms of lambda, it is given always, and this is nothing but the number of you can see metal trivalent, this is important. Okay, present in tetrahedral wide, present in tetrahedral wide, divided by total number of trivalent m+3 present in the lattice, present in lattice. Okay, that is called a spinal parameter, that is termed as the lambda. So that is nothing but number of trivalent and present in tetrahedral wide divided by total number of present in the lattice here. Okay, so this also you have to keep in the mind here. Okay, so very simple it is. And always you can see here, for example, if you take it here like m3O4. Okay, so so you can take it here like normal spinel here. So this normal spinel it is present -2 here is there, m+2. So f-2 is taking the place of FCC, and here m+2 is having the tetrahedral side, and here 2m+3 they are having the octahedral site here, octahedral site. Okay, M3O4. So one M is having +2 tetrahedral site, and 2M plus 3 in the octahedral sites here. Okay, now if you calculate the lambda value here, so how many, see, a number of M plus 3 ions present in the tetrahedral wide. Now you see tetrahedral wide, there is 0, it is M plus 2 here. Okay, so in this there is no tetrahedral wide, divided by total number of trivalent ions. So see, a total number of trivalent ion in this case, how many is 2, M plus 3 is 2, M plus 3 is the 2, so 2, so it becomes almost 0. Okay, so that is that shows that your the whatever this is there, it is a spinel. Okay, so this is how to identify whether the compound or given is a spinel or not. So if you calculate this now parameter, spinel parameter, then definitely you can see that this comes, since it is 0, it comes under spinel here. Okay, then how to understand this is complete inverse. Okay, complete inverse will be there. Again we will calculate here. So this is -2 FCC already we have done, and here M plus 2 in octahedral will be there, M plus 3 tetrahedral, and again here M plus 3 octahedral. Okay, there is a mixing here now here. Okay, so O minus 2 FCC complete inverse. Now M plus 2 in octahedral will be there, M plus 3 in tetrahedral, and M plus 3 in octahedral. That is a mixing here. So okay, so this is a conditional base. Now if you see the lambda here parameter, okay, so total number of M plus 3 present in tetrahedral whites. Now you see how many is there here tetrahedral whites. So 1 is present, MS plus 3 in tetrahedral 1, divided by total number of M plus 3, how much is there. Now you see here 1 is there, and here 1 is there, plus 3 plus 3. Okay, so 2, 1 by 2, that is your 0.5. So for complete inverse, so you can see lambda value is coming to 0.5. Now what is left now? So here spinel is over, and complete inverse spinel is over. Now left is what, your mixed. Okay, or mixed spinels, or mixed inverse, or they call it as a partial inverse. So partial inverse or mixed inverse, so when it will be there, when lambda value will be greater than 0 but less than 0.5, so this becomes a partial inverse. Okay, so this also you can be we can be helpful for solving some of the questions. Okay, like in some of the one of the paper, they have asked one question regarding this parameter, that is spinal parameter, that is NiFe2O4. Okay, so he has given lambda as 0.40. Okay, and he has asked you to calculate percentage of nickel plus 2 in tetrahedral wide. See, this is the concern. Okay, so he has given this spinel here, lambda value he has given, that is spinel parameter, but he is asking you percentage of nickel present in tetrahedral wide. Now you know what is lambda here. Lambda is nothing but number of trivalent ions in tetrahedral size divided by total number of trivalent in crystal lattice. Okay, so lambda already has given, that is your 0.40. Therefore 0.40 is equal to, we will take it as a x here. Okay, divided by how many, this is we don't know tetrahedral word, this only we have to calculate. We take it as a x here, and total number is for how many we have got here 2 here. Okay, so there is 2 trivalent ions, Fe plus 3. Now if you calculate this, it comes x value to be 0.80. Okay, or if you calculate into this percentage, because the asking percentage becomes 80%. Okay, now what is remained now here? Okay, so remained is what here, so 80% will be in the plus 3 state here. So this is your plus 3 state here, which we calculated here. Now remained, if you take 100%, remained will be what, 100 minus 80%, that is 20%. So that means your divalent ion whatever is present is in 20%, like this. Okay, so so whatever this tetrahedral site will be present, Ni plus 2, so it will be 20%. So like this, sometimes they asked the spinel parameter in some of the net examination. So that I think this is more than sufficient to understand the spinels. Okay, and spinel parameters, like what is normal spinel, inverse spinel, or mixed spinel according to spinel parameter. So whatever important part, if part of CSIR net will be there, is there, or the concept is there in the syllabus, so whole thing is covered in this video. Thank you.